Hello everyone, I hope you're all doing well. I'm going to solve one more problem on moments. We're going to be solving lots of problems on moments. Okay. Now in this problem, what I'm going to do is this. I'm going to solve this using both the scalar and the vector approach. Okay. So here is the problem. It's an interesting problem. Alright, so in this problem, I have a person who's holding a heavy object, and that person is, standing on the ground. And I'm going to draw that person to the best of my ability. Okay. So here is that person that I'm going to be talking about today. Okay, pretty long body. And let's see, I'm going to draw the hands of this person. Okay, so the hands of this person, the person is holding something, which means that, probably there is a force which is acting on the hands of this person. And then I'm going to draw the legs of this person as well. Okay, so starting from the hip joint, okay, so which is where probably this point where I've marked, I have the legs of the person which are coming out. Okay, and then the person is standing on some rough surface. Okay, probably ground, or maybe performing an experiment of some kind, who knows. And so here is the person. Okay, and the person is standing on ground. So as I said, the person is probably carrying something, and probably because of that there is a force acting on that person, and that's exactly what we're given. Okay, so here is the force acting on that person. This force, which I'm going to call as the force F, has a magnitude of 260 newtons. Okay, and then you're given a slope triangle that accompanies this force. As I said many times, even though these triangles may or may not look like right angle triangles, most times they do. They are right angle triangles. These are the slope triangles. Okay, we have spoken about slope triangles way earlier in the semester, so please go back and take a look at those kinds of problems. All right, so here is the point B. Okay, and here is what I call as the point A. Okay, so point A is where the force is acting, so this is the point of application. Application of the force. Okay, this is the point of interest, which is the point B here. Okay, so this is the point of interest. So this is probably the hip joint. Okay, and I'm given some distances here. Okay, from point B to point A, which I'm going to mark in a minute. Okay, so starting from here all the way to the point B, vertical and horizontal distances are given to me. Okay, so this is the vertical distance and this is the horizontal distance. I'm going to mark them as dotted lines, as you know by now. Okay, and these distances are 0.25 meters and 0.3 meters respectively. Okay, what am I supposed to do in this problem? Using both the scalar approach and the vector approach separately. Okay, so using the scalar approach and the vector approach separately, obtain moment about the point O due to the force F. Okay, so keywords here are, you're asked to use the scalar approach, which means you have to use the right hand rule, and then you have to use the vector approach, which means you have to use the idea of cross products. Okay, so maybe if you just want to make a note of that, this is by using the right hand rule. And when I say vector approach, you need to make use of the cross products. Okay, we will see what they are. And this is the person who is of interest to us. So my first situation in my mind, what I'm going to do is, okay, I'm going to take this person. Let me take only things that are of interest to me. Okay. All right. And then I'm going to bring that person down here. Okay. And you know what I'm going to do first, right? I'm going to set up the axes for this person. So I'm going to call the vertical direction as the y-axis. Okay, so here is the y-axis for me. Okay, then starting from the point B all the way on here, I'm going to draw the x-axis for this person. So maybe I should choose different colors for these things. I guess not. Doesn't let me do it. That's okay. Let me stick with this color. Okay, I'm stuck with this for life now. And then I'm going to take another line and draw it from here. Okay, so this is going to be the z-axis. And obviously you realize that this is a planar problem. Okay, so that's something you want to make a note of as well. So this is a planar problem. Or this is a problem in 2D. This is something you have to realize, okay, by looking at the problem. The problem may or may not let you know, but by looking at the problem, I see that the force is acting on the xy plane, then the distances are also in the xy directions, which means that this has to be a planar problem. So the direction of the moment is going to be either into or out of the page in the third direction. Okay, then as we typically do, we take this force and break it into its components. Okay, I'm going to use the scalar approach first, so that's something I got to specify here. So I'm going to use the scalar approach first. So scalar. And even in the vector approach, you will see that I will be breaking the force into its components. So this is going to help me in both the approaches. Okay, so I take this force and I break it into its components. So the first component is a vertical component. Okay, this is acting vertically this way. The second component is the horizontal component, which is acting as shown here at the point A. Point A is the point of application, so the components either meet there or set away from there. Okay, so the forces with their components are the following. So this is going to be 5 by 13 F. Okay, and this let me call it as the force Fx, because it's the x component, right? It's along the x direction. So this is going to be the force Fx, which is 5 by 13 F, and then this is the force Fy, which is 12 by 13 F. Okay, and then F is equal to 260 newtons. Then what do? Okay, how do I find the moment about the point B due to the force F? It's going to be the moment about the point B due to the force Fx and due to the force Fy, and we have to use the right hand rule. Okay, so it's a vector sum of these moments. Okay, so a moment about the point B due to the force F. The key idea is moment about B due to this force Fx, vector sum, moment about B due to the force Fy. Okay, and as you can see, what we need to do next is we need to find out, okay, what is the moment due to the force Fx and what is the moment due to the force Fy. And let me scoot down a little bit and let me write that here. So moment about B due to the force Fx, that's the first thing I'm going to write. This is the magnitude of the force, which is 5 by 13 F, okay, times the perpendicular distance. I want to write that 5 properly. So 5 by 13 F times the perpendicular distance from the force F to the point B. Look at this, look at this. So I take a line and I draw the line of action. I extend the line of action from the point B. I extend a line parallel to that force, and then I see that, okay, hey, this is the perpendicular distance between the force Fx and the point B. Okay, so this distance is going to be 0.25 meters. So this is going to be 0.25. I was writing all of these in the color blue, so let me continue with that. So this is 0.25. What is the direction? Right hand rule. Align the fingers of your right hand with the force Fx. Your palm should be facing the point B. You will see that your fingers are now drawing in a direction parallel to the x-axis above the point B. Curl your fingers. Direction of the thumb points out of the page. So this is going to be a positive moment. Then moment about B due to Fy. Okay, this is the moment of the y component of that force. And how are we going to do that? Look at this. I know the force, which is 12 by 13 times F, right? What is the perpendicular distance? From the point B, I draw a line parallel to the force Fy, which is already drawn in this black line here. So all I have to do is just complete this and then look at this distance here, which is 0.3 meters. And so this is a distance of 0.3 meters. Direction of this force. Use the right hand rule. If I use the right hand rule, align fingers with the force Fy. Your fingers are going to be twisted or contorted. You will feel a little bit of pain when you're doing this, okay, which tells you that, hey, there is something wrong with the direction of the moment. It's not the usual direction. So if I align the fingers with the force Fy, my palm facing the point B, my thumb, if I curl my fingers, is going to point into the page. So this is going to be minus K. Okay, so I have everything ready. All I have to do is, okay, moment about the point B is 5 by 13 times 260 times 0.25 K plus 12 by 13 times 260 times 0.3 times minus K. So plus K minus K, you can add them up. They're in the same direction, right? So MB due to F, if I do the computations, it's going to give me something that is approximately minus 47K, so many Newton meters. Okay, so this is the answer from the scalar approach. Okay, so this is from using the scalar approach. Okay, how do I do it using the vector approach? Okay, so now I'm going to do the vector approach. I'm going to write that down separately here. So okay, draw a line underneath there. This was the scalar approach. I'm going to take this creature from here, okay, this person. So I'm going to copy that person, bring that person down here. Okay, all right, so the first thing is I have my axis system as before. Okay, so there is nothing different from what I did for the axis. So this was the y-axis. It is always important to have the axes. Okay, this was the x-axis, okay, through the point of interest, and then I have the z-axis, which is coming out of the page. Okay, so this is the z-axis. Then I realized that, okay, hey, if I look at this force, if I broke it down into its components, right, as you know from the previous case, there was one component that was directed vertically down and the other component was pointing to the left. Okay, so this component was this Fx, which was 5 by 13 times the force F, and then this was Fy, which was 12 by 13 times the force F, right? Notice that the force Fx is pointing in the negative x direction, Fy is pointing in the negative y direction. This is a planar force. So my first step is write the force as a vector. Okay, so A, write the force as a vector. So that the force F is now going to be minus 5 by 13 F in the I, minus 12 by 13 F in the J, and 0K. Okay, which means that I can write this force as the following now. So the force F is going to be minus 100I if I do the substitutions, minus 240 J plus 0K, so many newtons. Okay, this is my first step. Then my second step is to see, okay, hey, I need to draw the position vector from the point of interest to any point in the line of action of the force. What is the best point here? It's point A, right? Point A is a point on the line of action of the force. Okay, so point A is the point of application, as you know. Let me also specify that here. So this is the point of application, point on line of action of the force F. This is the point of interest. Okay, that is the point of interest. So I'm going to draw a position vector. I'm running out of colors here, but I'm going to draw a position vector from the point of interest to the point of application of the force, okay, which is some point, and so my position vector is directed that way, okay. And if I have to just maybe do like a line sketch of this, right? So if here is the point B, okay, and then if here was the point A, okay, and then if these were the components of the forces that were acting at that particular point, okay, so that would be your fx and fy, okay. So this was fx and then this was fy, okay. And then my position vector is going to be from the point B to the point A, okay. So this is going to be r starting from the point B going to the point A, so RBA, okay. So this is r maybe let me, so this guy here is RBA, okay. And I want to show that that this is just a blown up view of what we are seeing there. So let me put a box around it, okay, with your permission. Bear with me, please. I'm going to copy that and paste that down here too, and maybe complete that hopefully before the day ends, okay. And I'm going to take that and join that, okay. So this is just an enlarged view, okay. And so that is the position vector. So how do I find the coordinates of the position? How do I find the position vector? I need to find the coordinates of the point B, right? Point B is at the origin, so the coordinates of point B are easily written as 0, 0, and 0. How about the coordinates of point A? Look at the point A. I have to move 0.3 meters in the x, 0.25 meters in the y, and nothing in the z. So this is going to be 0.3, 0.25, and 0, so many meters, right? Which means that I can find the position vector fairly easily. Okay, so draw position vector from, okay, point of interest to any point on line of action of the force. Okay, in this problem I know only the coordinate of point A. Okay, so in this problem we only know coordinates of the point A, which means that we draw position vector from B to A. Okay, that's important. And so this is going to be RBA, and if I look at the coordinates of BA, it's the coordinates of the last point minus the first point, so that's going to be 0.3i, 0.25j, and then 0k, so many meters. Okay, so I have two important pieces of information here. I have the force F here, okay, and then I have the position vector here. And then my third step is this, okay, to find the moment, MB due to the force F. Here is what I do. I take the cross product of the position vector with the force vector. Okay, it is always position vector crossed with force vector. Okay, this is something that I want you to really understand. Okay, so this is always, and maybe I'll just write that in capital letters. Okay, always position vector crossed with the force vector. Okay, it is never anything else. If you do anything else, then that is going to give you garbage, which we don't like typically, and we throw off, right? So I urge you to please keep this point very carefully in your mind. How do I draw the position vector? I draw the position vector from the point of interest to any point on the line of action of the force. Of course, I have to be careful because I can't just draw it willy-nilly to some point where I don't know the coordinates. So in this particular problem, since you know only the coordinates of the point A in this particular problem, so my position vector is going to be from B to A. Okay, so if I do the cross product, here is what I end up getting. Okay, so I'm going to set up the determinant. Okay, the first row of the determinant is going to be occupied by the unit vectors I, J, and K. I close this. Then the second row is going to be occupied by the members of the position vector. So this is going to be 0.3, 0.25, and then 0. And then the third row is going to be occupied by the members of the force, which is minus 100, minus 240, and then 0. Okay. And I'm not going to go over the details of how to do a determinant. I'm going to be posting a set of written notes on this on Carmen. Okay, so I will post written notes on Carmen on how to compute cross products, how to compute determinants, I'm sorry. Okay, so if you do the math, then you will end up getting mv due to f, and what do you know? It's going to be the same thing. So let me write it this way. So it's going to be 0i, 0j minus 47k Newton meters, which is the exact same answer as we had from the scalar approach. So the approaches should not give you different answers. If they do, then something is wrong, right? So this is the same as that from the scalar approach. All right, so very last thing, in terms of maybe a recap of the problem. So here is what we do. If you're asked to do the scalar approach, you use the right hand rule. If you're asked to do the vector approach, you use the idea of cross products. Okay, so in the scalar approach, I have to use the right hand rule to come up with the directions of these things. Okay, so I use the right hand rule. Okay, to come up with the directions. And then in the vector approach, I have to use the idea of cross products. Okay, so I have to use the idea of cross products. Okay, and once you do this, typically the answer is going to be the same. If they are not the same, then there is something wrong, and that tells us, okay, there is something wrong in the way we have done. Okay, so thankfully the answers are the same here. I hope all of you stay safe. I'll see you in the next problem. Bye bye.